Hello, this is video Z, and I have some misgivings about video Z. I'm going to start off with an apology. I apologize to you, and no, it's not because my notes for video Z are exactly one line on this sheet of paper. It's that, here's the deal. In a regular offering of this course in a regular semester in a perfect world, this course would not be just about cranking out code as quick as you can and learning all the new syntax. It would also be about how to go about being creative and solving problems. In other words, you figure out things on your own. You solve the puzzles, you solve the problems, you develop an algorithm, you try it out, see if it works, it doesn't work, you go back, you try it again. But with our compressed time format, we really don't have much time. And the reason that I'm apologizing for video Z is because almost this entire video, once I get past my little soapbox speech here, is going to be doing what I would ask you to do in the regular semester. Try some examples, see if it works, see what you've got to keep up with, see what you can ignore, all that sort of stuff. Those are things that you should be figuring out. But because this is summer school or a compressed semester in the future, I'm cheating you out of some of your hard-earned tuition dollars because I'm going to be doing what I would hope that you would have done. Here's what you can do for me. To simulate the process of thinking about it and mulling it over and digesting it and coming up with a different approach, why not, as you're watching this video, looking for, okay, how do I just generate the code for crying out loud? Maybe just pause it or even stop watching it every now and then and see what your next steps would be in solving this problem. The reason I've only got one line on my piece of paper is I'm going to try to emulate the thought process of how on earth are we going to do something like Program 3. All we've done so far is read through Program 3. We've got a vague idea of how to maybe to write a separate class by looking at the TV class example. How on earth are we going to do a bounded buffer? B-O-U-N-D-E-D, buffer. Especially when we don't even know what the hey it is. Well, remember from the last video, way back then, we talked about stacks and queues. Bounded buffer is a special case of a queue. In fact, an alternative name for it is a circular queue, which I think is a little mysterious and cryptic because almost always a bounded buffer will be implemented with an array. And it's kind of hard for me to think of an array that I always draw linearly. Think of that as a circle. But the reason it's bounded is because there's an upper limit. There's a maximum number of things that can be in the queue at one time. In our case, it's 5. And for Program 3, and you can hard code that in there. Symbolic constants are silly hard to do in inside classes if you have to know it when you're defining your private variables. So just go ahead and stick a 5 in there in those square brackets for your array. And you'll know what I'm talking about when you actually try to implement this stuff. But a bounded buffer, I'm going to just call this scratch work. This is me. This is me emulating what you would do if you had the time to go off and sit under a tree with your clipboard or notebook or whatever and think deep thoughts and just do some examples by hand and see what things you sort of have to keep up with and what things you can let go. Remember, a queue has to have 2 operations. It has to have insert and remove. So I'm going to do some inserts. In fact, I'm going to stick with colors because I like colors. Could you tell? Red, orange, yellow, green, 1, 2, 3, 4, blue, indigo. Sorry, indigo. You got abused last time, or you got left out. You got ignored, violet. Okay, so there's some things just to try out hypothetically an insert operation in a queue, and I've already given away one of the secrets, if it were a secret at all. A natural implementation for a bounded buffer, since we know in advance how big it's going to be, is to use an array. Now, actually, 5 is artificially small, but it's a lot easier to debug your program and figure out whether or not it works with 5 slots in your buffer than it is to do, say, oh, I don't know, 5,000 or 15,000 or whatever. So let's just stick with the 5. And here is my scratch work view of the array. 1, 2, 3, 4, 5. And orange. Insert orange. Whoops, no. How about red? Let's insert red. There. It's in the front of the line. What could be? Is that blur? Orange. I'm going to have to abbreviate because I made the slot so small. ORA is orange. Yellow is YEL. So far, so good, right? I mean, this is easy. I made a big deal of it at the beginning, and I have to apologize for my apology, I guess. And then green. Green. I should be doing this in a different color, I just now realized, and I will after I get a little further along. Blue. Man, indigo is a Rodney Dangerfield of the colors, isn't it? That might be a reference that you don't get, but gets no respect. Because indigo, you don't get to go. I didn't even plan that. I feel so clever right now. Indigo, our bounded buffer is maxed out. There's no room. So this is going to get a return value of false, and so is violet. There's one situation we ran into. Mental note. Since insert could fail on the bounded buffer, I probably do need to return a Boolean value. And not just because it's required in assignment 3. It makes sense to return a Boolean value to say yes or no whether or not the insert operation was successful. So there's one thing figured out already just by doing this simple example. So, shall we continue? Let's. Let's do a remove operation. Does remove get anything? Well, yes. Red is right there. And red is used up. Now, here's something we're going to need to keep up with. Red is used up. So that's gone. Even though we can still see its little ghost right there, it's gone out of the buffer. We remove it and return it, and the main program got red and say, look, I got red out of my bounded buffer. And when it calls remove again, it's going to get orange. It's abbreviated inside the buffer because there's no space, but it got orange. Now then, it might feel like this would have been simpler to get orange, and even the next one, I'll go ahead and get yellow. Remove, get yellow. You might already be thinking, you know what? I think I can finesse my way through this problem of keeping up where the next one to get is. I'll just move them up to the front of the line. What could be more natural? If the people in front of you at the movies, they've already gone through the line, then you're at the front of the line. Here's the problem with that. Remember, this is artificially small just to make it manageable in program 3. But if we've got 5,000 or even worse, 50,000 elements filled in this buffer, and every time we remove one little thing that's in the buffer, we move everything else, that is wildly inefficient, meaning that it is really going to slow down your program. To do one little operation of remove to get something out, to move everything over in the array, has this massive domino effect. Orange would go to the first, yellow would go to the next, green would go to the next, blue would go to the next. And then the next time we do a remove and get orange, then yellow has to go to the next, green goes to the next. I'm bored of hearing myself talk about it already. So the standard implementation, the recommended implementation, the efficient implementation is not to do that. No data movement that's not necessary, please. So we leave things where they are. These are just dead. Those we can still see them. And you know what? Here's a weird thing. We might decide later on, after we're going through this example, we might decide just to leave those there anyway. And just make sure we keep up with who's next. Oh. Who's next? That would actually almost be a good name for a private variable. You could use that, a state variable. Who's next? It's going to be easier to keep up with who's next if I actually have the index numbers up here. 0, 1, 2, 3, 4, and that's the end if I've got 5 things. And my who's next variable could keep up with who's next. Of course it could. Initially, who's next is 0. They're the first ones in there. After we've got that, then we just bump up who's next. Who's next equals 1. After that, you get the pattern. Rapidly, we see a pattern developing. Who's next would be 2. Now, the who's next, I will catch up to where I was. Who's next? And no, I don't know that that's a very good name for your private variable. But now that I've already broken the seal on it, I guess you could use it if you wanted to. Who's next at this point? You know what? I'm going to reverse engineer the history as well. It was initially 0. That's where the first thing's going to come out of the buffer. Then it became 1. Then it became 2. Now it's 3. And I'm all caught up. Who's next is 3. So I get green. Have I gotten green? No. If I do a remove, I get green. And I'll try out my new who's next private variable. This, remember, if that's a private state variable, that's hidden inside my bounded buffer object. The main program is not aware that a who's next variable even exists. It has no business tinkering with it. Get your hands off my private variables. So, 3, I'm just going to use that. So I've used up the green, and who's next has got to be bumped up to 4. Okay? Now, before I go any further and have to deal with this boundary condition, let's say that somebody else comes along and does an insert. Are there any colors left? Red, orange, yellow, green, blue, indigo, violet. You know what? That's going to confuse things. I was going to give indigo a second chance, but this is just not indigo's day. So indigo has to stay out. Let's insert gray. After blue, it has to go behind blue. Here's why this is alternatively called a circular queue. We reuse slots that have been vacated. The next available slot initially was the very first slot, then that one, then that one, then that one, then that one, and then there is no slot number 5. It wraps around like a circle. It's as if, visualize this, it's as if slot 0 is appended after slot 4. So we can think of this array as being repeated infinitely. 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. The next available slot to insert something in the array is 0, gray. There is room in the array because we've cleared out some slots with remove operations. Gray is in there. I'm going to run out of colors. Insert pink. Well, you know what? It doesn't look like who's next is helping out at all here. How did we know that 0 was going to be where gray goes? And now that gray's in there, how are we going to know that slot 1 is where pink should go? Pause, think about that. Well, pink should go after gray. If we think of this as a circular line that goes off infinitely in a straight line, then pink should go after gray. And in fact, that is where we want to put it. We want to put it, if there is a slot available, we want to put it in the next available slot. While you're doing it, here's what you're missing out on. And I am apologizing every few minutes. What you're missing out on is as you do these examples by hand, trying to figure out how the heck am I going to do this, then the need for your state variables in your class, those state variables are going to reveal themselves to you. I need a new variable to keep up with where the next available slot in the array is, the next available slot in my buffer. This does not tell me that. This tells me who's the next winner in the buffer that gets to get out of the buffer and go back and join everybody in the main program. Go to the party. I need a separate variable to say where the next available slot is in the array. You know what? This has gotten so messed up. I'm going to erase the checks, erase the X's, erase this. You're not erasing. Whoops, gray and pink, I wanted to leave those down there. Gray, pink. Iteration 2. Now that I've realized I've got to keep up with more than just that one thing, I've also got to keep up with the next available slot. I'm going to go back and try my example again and see if those two variables are going to help me out. So, all this goes away. And you start a fresh array in your notes, in your scratch work, because here comes another example, same as the old example. And I'm not going to call it who's next. I've come up with the name because I don't want the names to be confusing at all. Who's next is actually next to remove. I like that name better. It's more boring, I know. But next to get. I think in program 3 even, it's called the get operation. Maybe a put operation and a get operation. The put is the insert operation. The get is the remove operation. So I'm going to call this variable next to get and next to put. And if I've got those function names wrong, I apologize, but map them over to whatever it says on the assignment 3 sheet. I don't have it memorized. So here we are. Let's see there. We've got 2 mouths to feed now. We've got 2 private variables that are going to be defined in the header, which means we'll want a non-empty constructor. We have to think deep thoughts. Well, let's see, the TV class, we initialize one of the variables to 1 and the other one to 5. Oh my goodness gracious, that is the most ridiculous thing that I've probably said all summer school so far. We don't want to initialize those to arbitrary numbers. We want them to make sense. The next thing that we're going to get, even though there's nothing there, is going to be in slot 0. The next place to put something is going to be slot 0. I said I was going to do the same sequence. I accidentally lied. All my lies are accidental, by the way. I'm going to start with the remove operation. Now, I lied again. I don't want to deal with that right now because next to get is saying, get me something out of slot 0. So when I call remove, it's going to try to get something out of there. And right now, there's garbage. There's another ugly boundary condition. I'll deal with that later. I'll try out. I'll go back and put that back in later. But put that in the background. Think about that. Maybe pause the video and think about that. What am I going to do if the idiot user tries to remove something before they put anything in the buffer? We'll deal with things one at a time. Here we go. Insert red. Next to put. This is where I want to put it. Red. Now, the act of putting, should that change these variables? Should they bump up to 1? Next to get certainly should not change. Think about these things really hard. Next to get is where the next thing is going to come out of the buffer when they call remove. There's nothing but garbage in slot 1. We're not going to remove anything from there. Next to put, now we do need to bump this up. Look at this. Think deep thoughts, profound thoughts. Why does this one need to change but not that one? Well, this is a separate thing. Next to put is the next available slot in the buffer. So red is in there. Check. All over again. Orange. Next to put, we put orange in there. O-R-A, short for orange. Also, we've got a bump up next to put. Yellow. Yellow goes in slot 2. Rapidly again, we see a pattern developing. Bump up next to put. Now it's 3. Green. Green goes in slot next to put, which is 3. We're on a roll. Things are looking good. Green's gone. Blue. Put blue in there. Oh, I forgot that. Yeah, sorry about that. When I put green in there in the next to put slot 3, then I need to bump this up. That's part of the insert or the put operation, is to bump up whoever's keeping up with where the next available slot is. Who's next? Was that the who's next? I don't remember. Okay, the blue. Blue goes in slot 4.